for the continuation of the topic application of integral with a subtopic centroid of a plane, or finding the center of mass of a lamina. Okay, so let's just have a short review of the formulas that we will be using, which is the coordinate, the center of the lamina, sorry, the center of mass of the lamina, which is x bar and y bar, wherein x bar, it has a formula of this, and y bar has a formula here. Okay, and instead of using the total mass, we are now using the area of the region given in a curve, since we already canceled the density. Okay, the density of the given lamina on both numerator and denominator. So what we got is just the area at the denominator. Okay, so let's start with our discussion with example number one. Example number one, find the centroid of the region bounded by the curves y is equal to x squared minus 1 and y is equal to 2x minus 1. So the first thing that we need to do is to sketch the graph. Okay, so let's sketch the graph here. Oh, wait a moment. There we go. There we go. So this is our 1, 1, 1, and 1. Sorry, negative 1. 1 and negative 1. Okay, and our equations, the functions that we are going to deal with are x squared minus 1, and let's say that this is y is equal to 2x minus 1. All right, and let's say this is our f, and let's say this is our g. Okay, so let's sketch the graph of the given functions. Let's use this. Let's use magenta for f of x, and let's sketch the graph of this y is equal to x squared minus 1. X squared minus 1 is a parabola that opens upward, and its vertex is at negative 0, negative 1, or at the y-axis, and it intersects the x-axis at negative and positive 1. There we go. Okay, so let's sketch the graph of the parabola. There we go, and then here on the side. All right, so however, for the other graph, let's use cyan for g of x. Okay, and the point of intersection of 2x minus 1 in the xy plane at the axis are the following. So it intersects the point 0, negative 1 as well, and 1/2 here. All right, so if we're going to sketch the graph, that's somewhere like this. Okay, here we go. That's much better. And they intersect at this point and at this point. All right, so this is our g of x, and our magenta is f of x. Okay, here we go. So we have already sketched the graph, and what we need to do is to find the centroid. Okay, the centroid, or the center of the mass of lamina. And as I discussed in part 1 of this video, centroid, because we're just talking of a plane, okay? While center of the mass of the lamina, we should be talking about a plane also, okay? Centroid. Yes, okay, it's a plane. So again, centroid of the region bounded by the curves is just the same as the center of mass of the lamina. Okay, so all right, now for us to identify the centroid, now let's uh, draw or construct the rectangular representative of the given area. Okay, so let's say that the point is here, right? And we call this point as xy, something like that. That's the center of the rectangular representative that we have here in this region. Okay, and we know that there are n numbers of rectangular representative, and as the number of, or as the value of n goes higher and higher, now the approximated value of the centroid or the center and even the area are getting closer to the actual value of the centroid and the area respectively. Okay, so we want to make this as we want to get the exact area and centroid. So what we need to do is to make an infinite number of rectangular representative of the areas and the centroid here. Okay, so now let's identify the steps for us to find the centroid. Now, step number one, we need to find the area. Solve for area. Step two, solve for m sub x, or the moments about the x-axis. And S3, or step three, the moment about the y-axis, or the m sub y. Okay. And for us to solve step number four, we have to solve for the centroid with the use of the formula here. All right. So let's do step number one. Step number one is solving for the area of the given region. So to solve for the area of the given region, we're going to use this rectangular representative that we draw, and these are the x, all right? And for us to identify the height, so to find the area of this rectangular representative, that's the area, area is equal to length times width, okay? And we know that the width is dx, and the length is equal to, what's that? The difference of g, that's the higher, minus f. Okay, sorry. Yeah, so g minus f times dx, and we will get the area. This is g. Okay, so let's solve that here. So that's the integral of g minus f dx. Right. Why is it that g is on the first term and f is on the second? Because g is on the upper part or above the the f of x. Okay. And it was discussed when we discussed about area of the region bounded by the curves. So the boundaries are, since it's dx, we're going to get the x coordinates of these 2 points. We have here 0, 1, and this one is, what's this? Oh, we haven't solved for the point of intersection yet. All right, for the point of intersection of these two curves, now we can solve for x when we equate them. So this is x squared minus 1 equals 2x minus 1, which is equal to x squared minus 2x is equal to 0, and x is equal to, or x times x minus 2 equal 0. Therefore, x is equal to 0 and 2. Okay, so if we have, if x is equal to 0 and 2, y is equal to -1, and x is equal to 3. So these are the points of intersections. Okay, so this one is 2, 3. All right. Okay, that's basic for everyone. Okay, so therefore our boundaries will be coming from 0 to 2, right? Because of the x. So 0 to 2. Okay, here we go. So let's substitute. the integral from 0 to 2. Our g is 2x minus 1 minus our f is x squared minus 1 d, oh, dx. And this becomes the integral from 0 to 2, 2x minus 1 minus x squared plus 1 dx. So this becomes 2, 0. I can cancel this. So this becomes 2x plus, oh, sorry, that's minus. So let's erase that. That's minus, right? That's minus x squared dx. Okay, here we go. So let's move on. So we have the integral, sorry, let's integrate. We can now integrate this. Okay, so we have, let's integrate the terms. So the integral of 2x is just x squared. And the integral of negative x squared is negative x cubed over 3 to be evaluated from 2 to 0 to 2, I mean. Okay, since the lower boundary is 0, so we're just going to take good care of the 2 here. So this becomes 4 minus 8 over 3. This is 12 minus 8, that's 4 over 3, right? Okay, so the area is equal to 4 over 3. Okay, so we have already solved for the area of the given region. So let's work on the step number 2. Our step number 2 is, all right, let's just check what we have already done. So we're done with this. We're now on step number 2, and we're solving for sub x, or the moment about the x-axis. Okay, so we have, oh, sorry. In step number 2, okay, we're solving for the moment about the x-axis. And we know that the moment is equal to m sub I, or the mass of a certain specific rectangular representative times the distance, okay, to the origin, right, or to the axis that we're referring to, which is the x-axis. Okay, so we're going to use the graph here. All right, so again, this is our rectangular representative, and this is our point. Let me use another color for the point. Let's use magenta here. Okay, this is our point. This is with respect to what? With respect to the x-axis, right? Okay, since the graph is so small, now let's try sketching the graph on its place. Okay, let's try sketching it here. Okay, here we go. So let's say that this is the graph, all right? A bigger graph here. So let's sketch the rectangular representative. Okay, and this is our center, all right? The center of mass of the lamina here in this rectangular representative. Again, the center of lamina here in the rectangular representative. Again, this is our xy, just like x bar, y bar, I. Okay, and these are dx. All right, here we go. So here, what we're going to do is we're going to identify the mass, I mean the moment about the x-axis by identifying the mass of this object, this rectangular coordinate, rectangular representative and its distance with respect to the x-axis. So we know that our mass is equal to the density times the area. So therefore, this is equal to density areas of I and the distance from the x-axis. So the first thing that we need to do is to find the area of this rectangular representative. All right, so the area of this rectangular representative is just equal to length times width, and we know that the length is just the difference of two functions. This is our g and this is our f. So this is g minus f times the width, which is dx. Okay, so that's raw g minus f dx, and our d sub I, or the distance from the x-axis. Okay, let's sketch that so as everyone could understand. Okay, what is the distance of the center of mass of the lamina, sorry, of the rectangular representative to the x-axis? Yeah, something like that. And we know that this is the center of this rectangular representative. So since it's the center of the rectangular representative, so we're just going to get it's just like finding the midpoint between these 2 points here. Okay, so from the G, or from the line to the curve or the parabola. All right, so sorry. So it's just like we are getting the midpoint, as we discussed before in part 1. All right, so therefore the distance here is, okay, this is the midpoint, and to get the midpoint we have g plus f over 2. All right, and if we're going to rewrite this would be raw g minus f times g plus f over 2 dx. Okay, and if you know the formula, if you already memorize the formula, then you can go directly to the formula. But I prefer deriving it, because sometimes the formula doesn't really work. Okay, sometimes, especially if the graph is quite complicated or complex. So the moment about the x-axis is equal to 1 over 2. I converted the denominator as the coefficient of the integral. Okay, raw g minus f and g plus f dx. Actually, you can rewrite this integral expression as the g squared minus f squared, and then the rho can be placed here as the coefficient because rho is constant. All right, so let's write the formula here. So m sub x is equal to rho over 2 the integral from 0. Oh, sorry. We have from 0, -1, and this one is this is 2, 3, right? So our boundaries are from, let's say, 0 to 2. 0 to 2, correct. Okay, 0 to 2. Okay, and the formula, we have g minus f and g plus f dx. Okay. Okay, and let's now substitute the values of the functions g and f. So raw over 2 from 0 to 2, and rg is, what is rg? Our g is the line, which is 2x. G is here, which is 2x minus 1. All right, so that's 2x minus 1 minus the function x squared minus 1. Okay, or we can just square them up. And here we have, what's this? We have 2x minus 1 minus x squared minus 1 dx. All right, here we go. So we're now ready to simplify the expression. Rho over 2 from 0 to 2, and simplify. This becomes what? 2x minus x squared times, I can cancel 1, right? This one is 2x negative. Oh, this one is positive. Okay, 2x plus x squared minus 1, right? If I'm not mistaken. Yeah, we're just adding up the numbers. Okay, here. Okay, so we need to get the product of this. All right, this is quite long. So raw over 2, 2, 0, and let me just get the product. Okay, let me just pause the video and get the. All right, so after multiplying this, we got a negative, let me write it down, negative x raised to 4 plus 6x minus 4, 6x squared minus 4x. Okay, dx. All right, so we're now ready to integrate this. So we have, let me write this here, x of x is equal to p over 2, or the raw over 2. Okay, and let's take the integral of the terms. So the integral here is negative x raised to 5, negative x raised to 5 over 5 plus 2x cubed, right? Here we have 2, and this one is negative 2x squared minus 2x squared, sorry, and from 0 to 2. Okay, so let's evaluate. Again, we're not going to use 0 here because it will make the expression 0. So let's just use 2. So raw of 2, raw over 2 is equal to negative 32 over 5 plus 8. This is 8, yeah, 16 minus, what's this, 8. Okay. And to make it simpler, I can distribute this, the denominator, so as I could make the expression simple. So plus 8 minus 4, right? So this becomes raw. This is 4. So negative 16 plus 20, that's negative, that's 4 over 5. So m of x is equal to 4 raw over 5, if I'm not mistaken. Okay, so we already found the moment about the x-axis. So we're going to solve for the next, we're going to do the next step. Okay, so let's work on the third step, all right, which is finding the moment about the y-axis. Okay, here we go. So step number 3, let me just change the color. Okay, our step number 3 is finding the moment about the y-axis. All right, again, the formula for the moment is the n sub I, or the mass, times the distance of the point, okay, from the origin, or from the y-axis in this case. And we know that mass is equal to raw times the area. So our moment about the y-axis is equal to raw area sub I and the distance of I. So again, we will still be using the same graph. Okay, this graph. So the area will still be the same. So that's G minus F times the delta X, or the dx. Okay, that's our area. The area is this. So since we're dealing with the same rectangular representative, therefore its area still the same as this one. Okay, and next one is our distance from the origin, or from the axis. Our axis is y. So let's write that here and check the graph. So since our reference is the y-axis, okay, so this is the point, and we want to identify its distance from the y-axis. And since this is our x, okay, this is our x, so therefore this is also our x sub I. All right, so there we go. So this is our x, oh, sorry, this is our x as well, okay, or x sub I based on the point. However, we're now integrating it to the integral expression. That's why I'm not using anymore the x sub I or whatsoever. Okay, so let's simplify the given expression in order to use the integral. Okay, so we have the raw times x times g of x minus f of x dx, and this is now our integral from AB. This is our m sub y, or the moment about the y-axis. So we knew that rho here is constant or uniform. So it is considered as a constant. So just take it as a coefficient of the given integral. So since we're still dealing with the vertical rectangular representatives, so we're talking about the x coordinates of the point of intersections, or the points of intersection, which are 0 and 2, or from 0 to 2. Okay, 0 to 2, and copy. All right, so x, and our g of x is the line, right? That's 2x minus 1, if I'm not mistaken. Yeah, 2x minus 1. Oh, 2x minus 1. Okay. And our f of x is x squared minus 1, if I'm not mistaken, with respect to x. Okay, so we are now ready to integrate this. I mean, simplify and integrate afterwards. So let's continue. So at the moment, about the y-axis is equal to rho times the integral from 0 to 2 x. Let's simplify. This is, oh, I can cancel out the 1 here. So 2x minus x squared minus x squared dx. I hope everyone could still, okay, copy and follow. So let's simplify again. So rho from 0 to 2, 2x squared minus x cubed dx. So let's integrate rho. This is 2x cubed over 3, x4 over 4 from 0 to 2. Again, we disregard 0 here because it will just make the expression 0. So let's just substitute 2. So this becomes 816 over 3 minus 4, right? And let's simplify. So rho is equal to 12, 4 over 3. 12, yeah, 4 over 3. So therefore, our m sub y is equal to 4 rho over 3. Okay, so we have already found m sub y, and we're done step number 3. And step number 4, we need to identify our center, or the centroid. There we go. So here, we know that x bar, okay, the x coordinate of the centroid is equal to mass of, or the moment about the y-axis over the mass, or with the use of the formula, the shortcut, you can also use that. Okay, this formula. So it's just like we're going to remove the rho in the value. So we have m sub y is equal to, what's that? M sub y is 4p, 4/3. Okay, and again, the formula is area instead of m, based on the formula. which is coming from this expression, right? I hope you can still get my point here. So again, the integral, okay, or yeah, or we can follow this one. All right, we can still follow this, but we are going to include the raw, and the area here is just equal to, or the mass here is just equal to the area times the raw, right? Okay, the area is equal to, what's that? 4/3. Okay, again, the area is 4/3. 4/3 times the raw, because that's the formula for mass. Mass is a raw times area. Okay, so 4 raw over 3 over 4 raw over 3 is just equal to 1. Okay, and the y bar, or the ordinate of the center of mass of lamina is m x over n. Same thing. What is the value of the moment about the x-axis? That's 4 rho over 5. 4 rho over 5 over, this is 4/3 over a times rho, which is 4/5 times 3/4 is equal to 3/5. I can cancel this. All right, so therefore we have already found the x bar and the y bar, and this is 1 and this is 3/5. Okay, so the center of the center of mass of the lamina is at 1/3, 1 comma 3/5. Let's check 1 comma 3/5, correct? So 1 comma 3/5, where is that? 1 comma 3/5, somewhere here. Oh, somewhere here, right? That's 0.6. Oh, 0.6 is here. 1, is this one? Yeah, this is 1. 3/5 positive, it's here. Okay, somewhere here. All right, this is the center. Okay, maybe the figure that I drew is not so accurate. That's why we can find the center or the centroid here at this point, at this region. Okay, in this point. Okay, so let's go to the next slide. I mean, question. Okay, so we're going to, oh, I forgot. We're going to solve the same question or same problem with different approach. So instead of using vertical rectangular strip, now we will be using a horizontal rectangular strip. Okay, so let's do it here on the next slide. There we go. So using, let me just change. Okay, so using horizontal. Oh no, horizontal rectangular representative. All right, so let me just draw the figure first, I mean the graph. Okay. Okay, so this is now the graph of our functions. I just copied a graph. All right, I think this graph is more accurate than the one I did before. Okay, so let's copy the problem again. Y is equal to x squared minus 1, and y is equal to 2x minus 1. So our, what's this? Our cyan is the line. This is our g of x. And our white one, the white one is the f of x. All right. It doesn't really matter which one is f or g, as long as you know how to use them and when to use them. So f of x. Okay, here we go. And we are going to identify the rectangular representative. Okay, let's use magenta, and this is our rectangular representative. There we go. And let's identify that the center of the centroid of the rectangular representative is here. And let's identify it as x. Of course, it's the x I, oh no, x, sorry, x bar I and y bar I. All right. And same thing, we're going to use 4 steps here. We're going to identify, so let me just, right. So step number 1, identify the area. And step number 2, we're going to identify the m sub x. Step number 3, m sub y. And step number 4, we have the center of mass of the lamina. Okay, and this is our lamina, the whole graph or the whole region. Okay, and here we already knew that the graph or the area is equal to, what's the area again that we solved? That's 4/3, but let's try solving it with the use of the horizontal rectangular strip. Okay, so since this is horizontal, therefore these are dy, right? Okay, so let's solve for the area. And for the area, oops, okay, step number 1, solving for the area. Area is equal to length times width, okay? And our length is equal to the difference of these two. So our length is equal to this is our g of x, and this is our f of x, right? So this is, since g is on the left and f is on the right, therefore we're going to start with f, x minus g of x. Okay, so let's write it here. The length is f minus g, and our width is our dy, because that's how that's the width of the rectangular representative, and the length is here, the length, and this is the width, right? Okay, and dy. Okay, here we go. So let's use the integral. That's f minus g dy. And again, our point of intersections are, or the points of intersection are, we have a 0, -1, and here is 2, 3. All right, so therefore, since it's dy, we're going to start from -1 to 3, -1 to 3. Okay, so let's substitute -1 to 3. And our f again is our curve of the parabola, so x squared minus 1 minus the g, which is 2x minus 1 dy. Oh, okay. So since it is expressed in terms of y, so therefore we need to express the function in terms of y as well. Okay, so function of x in terms of y. That's why we need to rewrite this in terms of y, a function of x in terms of y. So let's do that here. Okay, let's do that here. So this is equal to, oh no, my pen. Okay, this is what's that? X is equal to the square root of y plus 1, right? So we're taking the positive values of x here, since we are dealing with positive values of x, including the 0, of course. And here, this becomes x is equal to, what's this? This is y plus 1 over 2. Okay, so we have now found the, all right, the functions, okay, in terms of x. And again, this is our f of y, and this is our g of y. Okay, so there we go. All right, so we're going to change this. Sorry for that. We're going to change this in terms of y, because we are talking about dy, and we are using horizontal rectangular strip. So, okay, I almost forgot that. Okay, you will be reminded by writing dy, okay, along the process of the solution. So this is equal to the integral -1, 3, and this is f of y. Our f of y is the square root of y plus 1 All right, and minus, this is y plus 1 all over 2 dy. Okay, so this is how we're going to solve for the area of the given region. Okay, so let's proceed. All right. However, we have already solved the area of the region. Since we're dealing with the same region, therefore, we knew that its area is 4/3. Correct? Okay, let's check that. The area, yeah, it's 4/3. So if we're going to simplify this and integrate this and evaluate at the same time, then you'll get a 4/3 answer for the area. So we're not going to do that since our main problem here is to use the horizontal rectangular strip in finding the moments or the center of mass of the lamina. Okay, so we're done with step number 1. Let's go to step number 2, finding the moment about the x-axis. Okay, and okay, let's go back to the formula. Again, guys, the formula here is just equal to m sub I and d sub I, where m is the mass, which is equal to raw area, raw times the area. So this is raw times the area sub I, area of the rectangular strip, horizontal. Okay, horizontal rectangular strip, the horizontal one, and its distance from the axis. It could be the y or the x. It depends. Okay. So there we go, raw. And how to find the area? We have already found the area here, correct? And that's f minus g. So we're just going to copy that. So f minus g, all right, times the delta, of course, delta y times the di. Okay, the distance from the, okay, here we go. So since it is m of x, or about the x-axis, so what is the distance of this point to the x-axis? Where can we find that? So let me illustrate. Yellow. Okay, what's the distance of this point to the x-axis here? All right, then it's just y, correct? It's just equal to y. Yeah, because this x, y, therefore it's just equal to yi actually. All right. Okay, so it's just simple. This is just equal to y. Okay, and let's simplify. We have the integral. Let's now use the integral. Raw y. Oh, sorry, my pen. Y and f of y minus g of y dy. All right, and how about our boundaries with respect to y? So that's -1 to 3. -1 to 3. Okay, there we go. Oh, I should be using white. Sorry. All right, so our expression now, the integral now is raw since it's constant from -1, 3, y. And what is our f of y? F of y is equal to the square root of y plus 1, square root of y plus 1 minus, and our g of y is y plus 1 all over 2. Y plus 1 all over 2 dy. Okay, so this is now our expression in finding the moment about the x-axis. All right, so let's go to the next slide to proceed with the. Okay. All right, so if we're going to solve this, or if we're going to integrate this, now the value of this is equal to, okay, let me just check. Let me check. Okay, since we have already discussed on how to integrate these functions, then okay, so let's say that we have already integrated this, and the answer here is 4/5. All right, so our moment about the x-axis is equal to 4/5. Of course, raw. Raw. Yeah. Okay. So this is our m of x. And now let's work on step number 3, which is the moments about the y-axis. And again, the formula here is MIDI And the formula for the mass is equal rho times the area I di. All right. And since we're talking about the same area, so that's what's that again? That's F minus G, F of Y minus G of Y. All right, and dy times the di. Okay. Now the distance of this point to the y in reference to the y-axis. So let's show that here. All right, the distance. Oh, let's use another color. Blue. Okay. So the distance of this point in reference to the y-axis here, this is equal to x, right? Okay, this is equal to x. However, we are expressing our expressions or factors or terms in terms of y. So what is the value of x here in terms of y? Okay, that's our problem. Now, for us to solve for the value of x here, now we know that this is the midpoint, okay, the center of the mass of this rectangular representative. Therefore, it's just good as saying as this is the midpoint between these 2 points. These 2 points, the point on the line here and the point here. So finding the midpoint, we have, to find the midpoint, we have, what's this? This is our, the curve is our Fy, f of y, sorry, f of y plus g of y all over 2. So this is our x. Okay, so we have already identified the x. Therefore, this is our f of y minus or plus g of y all over 2. All right, and okay, so let's simplify the expression, and we're now ready to express it in a form of integral. So we have rho times the integral, and we can over 2 because of the 2 here. Okay, we put this as a coefficient, and we can multiply fy minus gy and fy plus gy. So that's f square y minus g square of y dy from -1 to 3, if I'm not mistaken. Yeah, -1 to 3. So this is now our formula in finding the moment, okay, about the y-axis. Okay, so let's substitute. So the m sub y is equal to rho over 2, the integral from -1 to 3. All right, and our f is, what is our f? Our f is the y plus 1, the square root. Okay, so the square root y plus 1, of course it's squared, minus, that's y plus 1 over 2 squared dy. Okay, and if we're going to solve this integral, so let me solve that. And let me come back once I have already the answer. Okay, so upon solving this, we have, or I got 4/3. Or this equal to 4, sorry, my pen, 4 rho over 3. All right, this is my m sub y. Okay, if you want, guys, you can check the evaluation, the integral or the value of the integral here. All right, let kindly check if it's really 4 rho over 3. All right, so let's go to step number 4. Step number 4, we're now ready to solve for the center of mass of the lamina. All right, so our x bar is equal to the, right, so mass of y over, the moment of y, the moment of the moment about the y-axis over the mass is equal to, okay, the moment about the y is equal to 4p, or 4 rho over 3, wherein the mass the mass is equal to 4/3. Okay, I mean the area is equal to 4/3. But since mass is equal to, sorry for that, mass, oh no, my pen. Okay, mass is equal to rho times area. So therefore, this is, our area is equal to 4/3. So this is 4 rho over 3. This is 4 rho over 3, which is equal to 1. So therefore, this is 1. And for the y bar, or the ordinate of the center of mass of the lamina, we have m sub about the x-axis over n. Our m, the moment of x, m sub x is equal to 4 rho over 5. Okay, 4 rho over 5 over 4 rho over 3, which equal to 4 rho over 5 times 3 over 4 rho, which is equal to 3/5. Therefore, the coordinate of the center of the lamina is 3/5. So the center of mass of the lamina is now equal to 1, 3/5. Okay, so this is now the final answer. And let's check if we get the correct same answer. 1/3. Oh, where is the answer? Where is the answer for when we use the vertical? Oh, here we go. Here. All right, so we got the same answer, guys. So therefore, whichever formula you use, okay, or technique you use, or orientation for the rectangular representative, then you'll still get the same value. All right. So I hope everything is okay. And if you have some questions, please do comment under this video. Thank you.